Good afternoon, everyone. So imagine you fall into a magical world and was trapped inside the maze. You are all there alone and you have no power. And what is worse is that you find out the maze surrounding you is keeping changing. So for anyone who's seen the Harry Potter, the Goblet of Fire, you may notice that this maze is very similar to the last scene of the movie. And you may think this is actually like a fantasy world, but actually, in the study of quantum networks, this is a thing that we encountered frequently. My name is Zhuoxuan Xie. I'm a first-year physics PhD from Northwestern, and I'm studying the property and application of quantum networks. So in order to understand the problem, we should first talk about the basic idea of the networks. So a classical network consists of different dots, which in this case, we call them nodes. And between the nodes, we have the certain lines connecting them together, which in this case, we call them edges. And it is the collection of all the nodes and edges that is called a network. So this is the definition of a classical network. But what about quantum? So from quantum mechanics, we know that everything exists a probability to exist. And we just simply adopt this notion to our quantum network by saying that every edge is probabilistic. It means that every edge has a probability to exist, and it requires examination at each edge to confirm their existence in the network. So I know this is not much of an explanation, but allow me to give an example to illustrate the quantum behavior of the edges. So let's say you drive to work every day in the morning, and you just follow the everyday route you use to get to the work. But suddenly, you find out that ahead of you, the road is closed because of the road construction at this point, and you have to change your route because of this. So in this case, the road is closed, or in our world, the road is temporarily removed from the network because of something. And however, we cannot know the road construction before we leave the house. So we have to be at the construction scene to know that there's like a construction. This is actually very similar to the confirmation process we had in our quantum network. And also, although the road is like under construction, have like a relatively low probability, inside the quantum network, there is a very high probability that one road is like removed because of the quantum behavior of the edge. So we actually need to develop a new algorithm to deal with this kind of situation. Okay, so now we talk about the definition of a quantum network. But you might ask, why is this important? Besides that, this question is actually like a very interesting question. So why do we have to use quantum network instead of the classical network into application? So now, people hear like quantum a lot from like different places. Even in certain movies, although they didn't adopt the full picture of quantum mechanics into it. But we know that quantum is very likely to be the next revolution of technology in the near future. And with quantum, we can actually develop a lot of useful things. So first, we can have like a quantum computer, which we can just understand that it is a computer that is faster than any computers we have seen nowadays. And inside the quantum computers, there are quantum counterparts that is connected together, and we can approximate them to be like a quantum networks. And the other example is quantum internet, which is like a more direct use of quantum networks in this case. And for quantum internet, if you want to transport information between two nodes inside it, there is basically no delays at all. Okay, so let's now go back to our very first question, how to get out of a forever changing maze. So this question is actually very similar to the case of gets through a quantum network. And although this seems like a very complicated question, there's actually a very simple algorithm that could solve this, and people use that every day. So imagine you're here at one side of the city, and you want to go to your friend's house at the other side of the city. What should you do? So generally, you will pick up your phone, open the Google Map, and find the best way to get there, right? But let's go back a few decades. When there's no smartphone, not even the map of the city is published. What should you do in that case? So normally, people will just pick a direction of their friend's house and ask people along their way to their house to confirm the direction they choose. That's actually the algorithm we will use in our quantum network. So because of the quantum nature of each edge, we cannot go through the same path each time we go through the network. But we will rely on the relative position of each edge inside the network to guide through the network. So this will actually apply to the maze problem as well, where we just simply go to the intersection or go to the node in the maze where it's closest to the destination each time. And eventually, we will get out of the maze. However, this algorithm cannot directly be used inside quantum networks, because for sometimes the distance inside the quantum networks is not clearly defined. So take this as an example. So on this street, the distance between two houses is clearly defined by the straight line distance between those, like this. However, inside the random quantum networks, the nodes inside it may not have a straight line distance. For example, they may exist on a hyperbolic plane, so that it is very complicated to define the distance between them. And it is only with this kind of a clear definition of distance between nodes that we can actually use the algorithm I talked before. And this is actually what I did here. So my job is to, given any random network, I can develop a distance function that we can extract the distance between any two nodes from the function. And with this distance function, the algorithm can be used with no doubt. That's all from my presentation, and hope it will give more understanding of the quantum networks. And I wish that no one will be trapped in the maze anymore. Thank you very much.